Welcome to mini lecture 3 for module 5 on samples and sampling distributions. Often when we take a sample of data from a population, we can estimate things like the sample mean, but this estimate of the sample mean does not provide information on the exact value of the population mean. And a confidence interval is a range of scores that is expected with a specific confidence to capture a population level parameter. For example, mu, which is the population level mean. And why do we need confidence intervals? Well, confidence intervals allow us to account for random sampling error. For instance, in a previous mini lecture, you looked at many samples that were taken from a population, and each of those sample means were a little bit different, and none of them reflected the true population mean. So confidence interval allows us to take into account the variability that we find with different samples. However, it does not allow us to account for any type of bias. And remember that bias are measurements that would be not reflective of the true population mean. And a 95% confidence interval of the mean is defined as an interval estimate constructed such that the interval will include the population mean 95% of the time. Of course, you could have 90% confidence intervals, 99% confidence intervals, etc., and they would be expected to include the population mean for the same percentage of the time. So we need to take a little step back and look at a t-distribution, because these t-distributions are sampling distributions used for inferential statistics, and we need them because our sample sizes may vary and we won't actually know what the true population level standard deviation is. So these t-distributions were developed. And we'll talk a little bit about them now, and they'll come back when we end up doing t-tests as well. But we use them instead of the normal distribution because we do not know information about the standard deviation for the population. So they're used for establishing confidence intervals, for sample means, which is what we're going to be looking at today in this mini lecture, and then also for testing significant differences between sample means, and that'll be in an upcoming module. So here's an example of a table for the t-distribution. This is table D from your book. Along the left axis here, we see the degrees of freedom. We have probabilities shown on the horizontal axes. And when we're looking at confidence intervals, we're looking along the top for a two-tailed confidence interval. And then the values in the table are these critical t-values. So the table allows us to look at a t-value associated with the probability. So if we were interested in a 95% confidence interval, we would look in the 95% column. So we have confidence interval percentiles across the top, and the 95th percentile, for instance, would have an alpha level of 0.05, which we'll be referring to today and also in upcoming modules. So what you can see from this diagram looking at t-distributions is that the probability of a particular t-value changes with the degrees of freedom. So the important things to note here is that the area in white is 95% of the data, and then where the lines are on the vertical lines at the top panel at approximately 1.96 are the t-values for 95% of the data if we have an infinitely large sample size, and that these numbers change as our sample sizes and therefore degrees of freedom change. So with lower sample sizes, we'll have larger spreads of variation that would encompass that 95% of the data, because we would have lower levels of confidence. So when we look at a confidence interval for a population mean, we start with a sample from a population, and we would have our estimate of x bar. And then if we want to have a confidence interval, it would have some lower limit and an upper limit. And that our population estimate from our sample, so the sample mean would always be in the middle of that confidence interval. So the confidence interval is a range of values. Here I've shown them by LL representing the lower confidence interval limit and UL as the upper limit for the confidence interval surrounding the sample estimate that is likely to contain the population level parameter. And so to find the lower and upper confidence interval limits, we use this formula. So again, like I mentioned, X bar is our sample mean. That'll fall in the middle. The lower limit is then subtracting that t-value, which is based on our sample sizes, and the standard error of our sample mean. So that includes the variability. And the upper limit would be that mean value plus the t-statistic given our degrees of freedom and an alpha of 0.05, which is the same as the 95% confidence interval, and the standard error of our sample mean as well. So X bar is the sample mean, T sub alpha is the t-value associated with the particular probability. So 95% would have an alpha value of 0.05 because that's what's remaining that would be outside of our confidence interval. And then S sub X bar is the standard error of the mean, which is the standard deviation of the sample divided by the square root of the sample size. So now let's go through an example looking at constructing a confidence interval. So if we're going to make a confidence interval, imagine there was a study done on human body temperature and that this study is different from the one that's in the textbook, and we want to find a 95% confidence interval. So I'm just going to use CI for confidence interval of a sample with a mean value of 98.524 degrees Fahrenheit. The standard deviation of our sample is 0.678 degrees Fahrenheit, and our sample size is 25 individuals. So the first thing that we need to do, given this data, is to calculate the standard error of the mean. If you want to pause this and calculate that on your own and then check your work, feel free to do that. Otherwise, our standard error of our mean, recall, is going to be the standard deviation divided by the square root of our sample size. So it's 0.678 divided by the square root of 25, which we know is 5, and that will give us a value of 0.136 degrees Fahrenheit. So now the next step that we need to do, so we've calculated our standard error. Our next step is to find our value of T sub alpha, right? When we're going to be looking for T 0.05 because that coincides with our 95% confidence interval. If we look at the T distribution, so this is the same as what is in your textbook, and we want the 95% confidence interval, which is the same as an alpha of 0.05, and our degrees of freedom, remember, is going to be n minus 1. So degrees of freedom, n minus 1. We know that n is 25, so 25 minus 1 is 24. So we look at 24, and the column that we're interested in, an alpha of 0.05, and we have a value of 2.064. So we know that T sub alpha is 2.064, and now we can solve our equation. So for the lower limit, it's going to be X bar minus T sub alpha times our standard error. This is going to be equal to 98.524. That's the value we have of our mean, minus 2.064, which is the value we have for T, which is multiplied by our standard error, which is 1.36. And that gives us a lower limit of 98.243 degrees Fahrenheit. the upper limit is x bar plus t and the standard error. So now we have 98.524, and it's plus those other two values. So it's the same values as we had up here, because it's going to be symmetrical around our estimate of the mean. And now that we have this information, we can conclude that we are 95% confident that the true population mean for human body temperature lies within the interval between 98.243 degrees Fahrenheit and 98.804 degrees Fahrenheit. So that would create an interval. So our confidence interval in this case is going to be 98.243 degrees Fahrenheit to 98.804 degrees Fahrenheit. And when we look at confidence intervals, just to wrap this up, we have our population level distribution, and from that we can take a sample, right? And we have mu representing our population mean. All the bars below that, there's 20 bars there, and each of those represents a sample that's taken with the dot in the middle representing the sample mean. And when we have a 95% confidence intervals, and with the example here, we have means from 20 samples of the original population, and one of them will fall outside of the mean. So it will not include the mean, the population mean, in its estimate. So when you hear about statistics and they say 19 times out of 20, this is exactly what they're talking about. So when we have 95% confidence interval, 19 times out of 20, the interval that we have will contain the mean. So confidence intervals account for random sampling error but not bias, and a 90% confidence interval will be smaller than a 95% confidence interval. And that is because with a 90% confidence interval, only 18 times out of 20 will the interval contain the population parameter, right? So it would be smaller in that case. And increasing sample sizes will also decrease the size of the confidence interval. And that's because of two things. One is that if we increase the sample sizes, we'll have a smaller standard error with a larger sample size, and that the degrees of freedom will be larger, and then that will result in a smaller t-value. So if you look at the t-table, you can see that as our degrees of freedom, and I put in a big jump here, as our degrees of freedom get larger, that our t-values actually get smaller. So that is another reason why, as the sample sizes increase, that the confidence interval will get smaller. And that concludes this mini lecture.